So we're going to take a look at solving linear equations and inequalities today. And then you guys are going to do a little bit of practice. So one thing that we always want to remember when we're dealing with equations and also inequalities that we'll see in a few minutes is that order of operations. So you have that order of operations here outlined for you. So remember, the P is for parentheses, E for exponents, M for multiplication, D for division, A for addition, and S for subtraction. So if you're combining anything within a side of an equation, you're going to use that order. But then when you are trying to solve an equation, you're going to kind of look at that order of operations in reverse. So you'll undo any addition or subtraction first. Then you'll undo any multiplication or division, and then kind of continue from there. So first thing that you should always do is combine like terms within each side of the equation. Again, a term is just a variable. So if you see x multiple times within the same side of the equal sign, get those terms together first. And then what you do on one side of the equal sign also has to happen on the other side. We have to balance that equation. So if you're adding 7 on the left, you have to add 7 on the right. And then when we deal with solving inequalities, we essentially do the same thing that we do when we are solving equations. But there are a few things that we have to remember. We have to remember that we flip the inequality symbol if you are dividing by a negative. So only if the negative is what's moving to the other side is what causes you to flip that inequality symbol. And then we also could see, both with equations and inequalities, special cases. So if you simplify an equation or if you simplify an inequality and all of your variables disappear, you could be left with either a true or an untrue statement. So if you're left with an untrue statement, like this example here, where we have 5 is less than negative 2, 5 is not less than negative 2. So that's false, which tells us that we have no solution for that inequality. And it could be the same if we had an equation. If we were left with 5 equals negative 2, that's false. That would tell us that equation has no solution. And then here, as another example, again, all of those variables disappear, but we're left with a true scenario. So 8 is greater than 2. That is, in fact, true. 8's bigger than 2. So true statement tells us that we have infinitely many solutions. We can say infinitely many, or we could say all real numbers. And again, that's true with equations as well. So if you're left with a true statement with an equation like 0 equals 0, that is in fact true, and that would tell us that that equation has infinitely many solutions. So here's an example of solving an inequality, and that variable there is an L. So we have 3L minus 6 is greater than or equal to 8. And if we want to solve here, we would solve it just like we would an inequality. So I'm going to go ahead and just rewrite 3L minus 6 is greater than or equal to 8. Maybe I'm going to make this L a capital so that we don't think it's a 1. So we want to go ahead and isolate that L. We're going to undo any addition or subtraction first. So I'm going to go ahead and add 6 to both sides. So if 3L is greater than or equal to, I'm going to add that 8 and that 6 together to get 14. And then it's 3 times L, so I undo that multiplication with division, and then I'm left with L is greater than or equal to 14 thirds. And you can see here that none of the answer choices give decimal values, so we're not going to type that into a calculator or anything. We're going to leave it as 14 thirds, and then we have our solution here. Here's an example where we are solving an equation. This one's a little trickier because we are looking for what value of A does the equation have infinitely many solutions. So if we think about equations and inequalities that have infinitely many solutions, this means that we must end up with a true statement when all of our variables disappear. So again, for example, that would be 0 equals 0. So in order to see how we can make it a true statement, we can go ahead and simplify or clean up what's here a little bit. So on the left-hand side, I can combine this 3 with the negative 5 since those are like terms. So 3 minus 5 is going to give us negative 2. And then we've got that plus 10x. And then on the right-hand side, this x would be distributed to the parentheses, but I'm not really going to do anything with that right now because I'm going to just think of that a plus 1 is just some number times x, and then we've got a minus 2. So now we can go ahead and work with these constant terms. If I add 2 to both sides of my equation, I have 10x equals a plus 1 times x. And in order for these two sides to both be the same, I need it to say 10x equals 10x. So here, this 10 has to be equal to a plus 1. So I'm looking at 10 equal to a plus 1, and I might just be able to think about, okay, a has to be 9 because 9 plus 1 is going to match that 10. If not, I can go ahead and subtract 1 from each side to get that a equals 9. So a equals 9 is going to give us that solution. This one, again, was a little trickier. If you remembered that infinitely many solutions means that your variable term is going to disappear and that you're left with a true statement, that's kind of the key piece here. You then could try your answer choices to see what would work. But here, like say you used a 2, this is going to be a 20. And then over here, this is going to be a 3x. So those aren't going to end up canceling each other out. Same thing with the 7. This would be a 70. This would be an 8x. So not the same on both sides. And then finally with that 10 as well, you've got a 10x and then an 11x. So those aren't going to cancel each other out either. So you could work through the answer choices and do process of elimination with this one as well. So a few things about interpreting linear functions. This kind of deals with scenarios where you maybe have more of a application problem and they give you something that's in slope-intercept form here. So y equals mx plus b. Remember from Algebra 1 that your slope is m. So whatever your variable is multiplied by, that's your slope, and that's really your rate. So if you increase your x variable by 1, what's happening to y? Then your y-intercept, or b, is really your starting point. So here it says the value of y when x is 0, which is true, but in the kind of application process, we think of it as our start value. So take a second here to read example 3, and then we'll talk about the representation of some of those numbers in the equation. So this is something that's in slope-intercept form. It's different variables, but this L is really like saying y equals, here's your intercept because it's your constant term, so no variable attached. And then here's your slope because it's attached to your variable m. So here we're looking for what does 24 represent in the equation. So 24 is our y-intercept or our starting point. So that's just the initial length of the spring. If the problem had asked us instead what this 3.5 is representing, 3.5 is our rate. So 3.5 is telling us how much further that spring is stretching for each additional kilogram that's attached to the other end of the spring. So if we attach a 1 kilogram weight, then it's going to stretch another 3.5. If we attach a 2 kilogram weight, then it's going to stretch 2 times that 3.5, or 7. So here's another example. I'll give you guys a minute to read this one. So here, 3.5 is the number that we're interested in. And if we look up here, 3.5 is our slope because it's multiplied by that variable. So 3.5 is a rate. So if we go through and we look at our answer choices here, the first choice is just talking about how much it was in 1991. So that's not the right value because that would be like your start value, which in this case, we're looking at a rate and not the y-intercept. Same thing here, we're just talking about a one-time value. And here they're talking about a total increase between 1991 and 2008. So here the key of total is what's making that an incorrect choice because it's not, again, looking at a rate. Whereas this last choice here, it's 3.53 million each year or per year between 1991 and 2008. So that would be the correct choice there. One final problem here. Again, you can take a minute to read the scenario. Again, this one's a little trickier because of the division. I can rewrite this as g equals 15 minus 1 over 32 times m. And now it looks more like a linear equation. We have our rate here along with our y-intercept or start value. So here we're interested in the meaning of 32. So it does have to do with rate. So that's something that we can kind of use to help us narrow down our choices. So here it's saying it can hold 32 gallons of gas. That's not going to be it because that's, again, not referring to a rate. And then here, 32 miles on a tank of gas, that's not right, again, because it's not referring to a rate. Then we can look at our other two answer choices. And before we even do that, some of these you can just eliminate because they seem unreasonable. So if you had a car that could only go 32 miles on one tank of gas, that would be pretty fuel inefficient. And so that might be something that if you were totally stuck on this question, you say, okay, I'm going to throw that answer choice out just because I'm going to make an educated guess. And we also can kind of do the same thing with this first choice. She uses 32 gallons of gas per mile. It would cost you a ridiculous amount of money to travel anywhere if it was 32 gallons of gas to travel a mile. So we could eliminate that answer choice, again, just because it's totally unreasonable, which then in this case leaves us with this last choice. And I'll talk about why it's correct in a minute. If we were just talking about things being reasonable or unreasonable, we then would be left with this choice here. It would be reasonable to think that the gas tank could potentially hold 32 gallons of gas. It's a pretty big gas tank, but it could happen. And then this other one here at the bottom. In terms of the correct answer, again, this one's talking about a rate. It's the miles per gallon, so to the gallon referring to the rate, which makes that last choice correct. Maybe just even looking at the equation, you might jump straight to there because it's the miles per gallon. So kind of like we talk about gas as mpg, the per being the division. So you guys are going to go ahead and work on a couple of sections in Khan Academy that are going to deal with solving linear equations and linear inequalities, and then also interpreting linear equations. Both of those sections, you want to make sure that you're logged in when you do them so that I can see your results and put those scores in the gradebook for you. So here are those assignments. They are linked as well. Hopefully the links will work for you. You can let me know if they don't, and I can give you kind of an indirect way to get there. Again, your scores from Khan Academy, if you get at least 3 out of 5, you get full credit for the assignment. If you get less than 3 out of 5 correct, you can either take another attempt or you get half credit just for the attempt that you do. But again, you can take those sections as many times as you need. And as long as at some point you get a 3 out of 5, you'll get full credit for the assignment.